Our lecture on basic circuit analysis, and now we are looking at parallel circuits and Kirchhoff's laws. So our lecture number 4, well, this was for 26. So for a parallel circuit, the elements or components or branches in the network, or even networks themselves, they should have two common points that qualifies them to be in parallel, and because of that, they will have the same voltage. And the common point on the circuit is what we refer to as the node. So when we talk about a node in later chapters, we are talking about the common point in a circuit. So in that figure, there is node A and node B. Because R1 and R2 and the voltage source, they share node A and node B, then it means they are in parallel. Remember, as long as there is no component in between and the points are connected using a simple connecting wire, then that is the same point in the circuit. It makes a node, right? So in that case, all it means is that when you talk about R1 and R2 and the voltage source, they're in parallel, and we said if elements are in parallel, they have the same voltage across them. What it simply means is that the voltage across R1 is equal to the voltage across R2, which is equal to V. Now there's one thing that happens at a node. So at a node's voltages are the same, but then the currents will branch or divide into the different components or networks. Right? We'll talk about the current divider rule later, but that is what happens at a node. So as you can see, I1 is getting into node A. Then at node A, I1 is now branching into I is now branching into I1 and I2, and they come to node B, where they are again combined to form I. So that is a special thing that happens at a node. Then the resistance, if they're in parallel, they can also be combined into one resistor, and we say their equivalent resistor is RT. Then the number of resistors, we can call them N. What it simply means is that you can write an expression for RT, which is the total resistance of all the resistors that are in parallel to form one resistor. In that case, we have called it R tot. So what it means is that 1 over the total resistance of all the parallel resistance is equal to the sum of the inverses of all the resistors that are in parallel. But a special case is when all the resistors have the same value, you say R, then the total resistance RT is equal to R, which is the value of one resistor, over N that are in parallel. So if two resistors are in parallel, then we can now say 1 over RT is about 1 over R1 plus 1 over R2. And then if we make RT the subject of the formula there, we find out that the total resistance is called the product of the two resistors over the sum of the two resistors. That is a special case of two resistors in parallel. So what it simply means is that, let's say you have three networks which are in parallel. You can either use the total of the inverses, or you can use 1 over RT, which is what you see on our diagram there. So, diagram. So this will be your expression for two resistors that are in parallel. Now, there's also an inverse of resistance, which is called conductance. So for conductance now, if we call conductance G, then G is called 1 over R. That means if you know the total conductance, you can also know the total resistance. So looking at that, 1 over RT now becomes equal to the total conductance, becomes equal to 1 over R1 up to 1 over Rn. But we said G is equal to 1 over R. What it means is that the G total now is equal to the sum of G1 plus G2 plus G3 plus G4. Then if G1 up to whatever is the same value, say G, then the total conductance GT is called NG, right? So that is what you do. You add conductances when components are in in parallel. Then let's look at an example of a parallel circuit. Determine the resistance of and conductance of the circuit shown. So that circuit is having two components which are in parallel, R1 and R2. So for us to get RT, remember we said if there are two resistors that are in parallel, we say the product over the sum. So the product of 3 and 6 is 18, the sum is 9. So the total resistance is equal to 2 ohms. That's very simple. Then the total conductance is now becomes equal to 1 over the total resistance, that is 0.5 Siemens. So Siemens is the unit of conductance. Then determine the total resistance and conductance in the circuit shown. So in that case, if you look closely, you realize that at the top there, we still have one common point, which is a node, and we have another common point, which is a node. So what we can say is that R1, R2, and R3 are still in parallel, right? But for some of you, you would rather redraw it like this. So if you look at this point, right, this point is just this point that has been extended. If you look at it closely, we've just extended this point so that each resistor is in the vertical orientation. Otherwise, it's still the same circuit. I know it will confuse people later when we deal with other sides of circuits. But remember, if as long as there's no component in between, those components are still in parallel because they share the same nodes. So if you use conductance, this G1 is got 1 over 2, which is 0.5. G2 is got 1 over 4, which is 0.25. G3 is got 1 over 5, which is 0.2 Siemens. So the total conductance is the sum, which is 0.95. Then the resistance, you just take the inverse of the conductance, you get 1.053 ohms as your solution. So it is easier to use conductance to get resistance for parallel network than to use resistances. Right, so you can actually convert all the resistance to conductance, then you just add them up. Right, there are some numbers which will give you recurring figures, but normally for the easy ones, you can use that. Then I said at a node, current would divide or branch into different networks. So we now check what is called the current divider rule. So if you consider the circuit, you have a source E, then you have resistance R1 and R2, then you have a source current IS and the resistance I1 and I2, right? So what you are looking at now is, if you look at the voltages, V1 and V2, since those components parallel, that means V1 is equal to E and V2 is equal to E, right? So what we are saying is those values, they are the same because the components are in parallel. So that is what I was explaining, that they have the same voltage and got the same, share the same nodes A and B. So from Ohm's law, if you want to calculate I1, it's voltage over resistance, which equals V1 over R1, which is also equal to E over R1. And I2 is equal to V2 over R2, which is equal to E over R2. I'm sure you can see that. Then taking the resistance of the equation and multiplying both sides by voltage E, then you realize that E over RT becomes equal to 1 E plus R1, 1E plus over R2. So E over RT now, looking at this component, E over RT is the total current there, right? Then E over R1, which is V1 over R1, is the current I1. Then E over R2, which is what V2 over R2, is the current I2. So you can see that at a node, the current entering is equal to the current leaving. So IS got I1 plus I2, right? It can therefore be concluded that for a single supply source, the total source current equals the sum of branch currents. Then the magnitude of the current flow in each branch is determined by the resistance of each branch. So what it means is that the current flowing here, if you see E over R1, that means it's determined by the value of R1, and the current in that other branch is determined by over R2. So if you look closely at this component, you realize that The bigger the resistance, the smaller the current. The bigger the resistance, the smaller the current, because the resistance is in the denominator of the expression. And you can actually show that I1 can be evaluated as R2 over R1 plus R2 multiplied by IS. Anyway, I will not ask you to show the proof, but you can use that as the current divider rule for two resistors that are in parallel. So there is the current through a resistor, say R1, which is what I1, is equal to the value of the other resistor, which it is in parallel, over the sum of the two resistors multiplied by the supply current IS. So it is good practice to use this formula by combining resistance and remaining with one for which you want to calculate the current. So what we are saying is you can use this formula. Let's say you want to calculate the current through I1, yet on this side you have a lot of other resistances. You can combine all the resistances on the other side to make one resistor. Then you can just calculate I1 using the formula there. That's what we are referring to. Then the branch current can also be determined by the first calculating the total parallel resistance RT. Then the branch current IX is called RT over RX times IS. So I'm now saying if you have several resistances that are in parallel, right? You can simply calculate the total resistance RT. Then the current in a branch, say X is got 1, so the current I1 will now be equal to the total resistance over the resistance of the branch R1 multiplied by the supply current, and you get your total current flowing in that branch. So that's another method which I use for if you have more than two resistors in parallel. All right, so Rx will be the resistance of the branch you're trying to get the current. So let's take an example. We have that circuit with a source of 27 volts, and then current I1, I2, resistors 9 ohm and 18 ohm. So we want to calculate the total resistance and the total current in the branch through each resistor. So total resistance RT is got product over sum, which gives us 6 ohms for 9 and 18. Then the total current IS becomes called E over RT, which becomes 27 over 6, which is 4.5. Then using Ohm's law, I1 is got 27 over 9, and I2 is got 27 over 8, which is 1.5 and 3. You can also see that IS is got I1 plus I2. So our IS is 4.5, our I1 is 3, and our I2 is 1.5. So you can see that it sums up to the same thing. All right. So we take a break and we proceed after that. Right. Then we look at Kirchhoff's current law. Kirchhoff's current law, it said that the sum of currents entering and leaving a node or a junction is 0. Algebra, I'm sure you know it deals with signs. So current entering is called current leaving. So in that case, we have I1, I2, and I3 entering the node, and I4 and I5 leaving the node. So the sums of those should be equal to 0. So in that case, we've said current entering the node is a positive and current leaving the node is negative. Then we now go and give an example. For the given circuit, calculate I0. So if you look at that, it means 10 plus I0 should be equal to 4 plus 2, right? So you realize that I0 will become 6 minus 10, which is what, minus 4 amps. Remember, we said in our convention, current entering is positive, current leaving is negative. So if you say I0 is negative, right? We're saying I0 is minus 4A. What it simply means is that I0 is actually flowing in a direction different from what we are direction. So in reality, I0 is flowing in that direction. And if you write it that way, then it means I0 is equal to 4 amps if it is going in the direction of the arrow. But in this case, our I naught is minus 4 amps because of its direction. Remember, current is both magnitude and direction, right? So the new sign implies that what I was explaining there. Then the last thing we are going to look at in this section will be series parallel circuit. So you know that the components in a circuit will not be connected solely in parallel or in series, but there is a combination of series and parallel networks to form a circuit. So it is important for us to be able to resolve such. So if you look at that example, you can see that there are several components that are in parallel and other components that are in series. So if you want to simplify such a kind of circuit, what you simply do is that you identify which components are in parallel, which components are in series, then you combine them to form one resistance. For example, you can see that 9 and 11 are in series. You can combine them, and I'm sure you can see that it will give you 20 ohms there, right? Then you can see that these 4 and 5 are also in parallel. You can combine them. The 20 and the 10 are in parallel, you can combine them. Now, for the time being, those are the only components that are in parallel and in series. Don't try to see other components which do not fall into our definition of a parallel or a series. Simplifying those ones where the last example. Machine was not responding. We have to go where we were so that we finish off. Right. Networks. Then after we'll proceed the other sections. Right. This is where we were. So we're calculating all the resistances. I think so. In total, we got the 30 amps. So to calculate the interconductors, we work backwards, right? So like I was now explaining, now work backwards. From your 30, you see the combination of this. You branch your current. Here you branch your current. Your solution. Method number 2, the one of V1 and V2. I personally would not want to use that because it's more. Then in conclusion, you can see that the components or networks are in parallel. They have 2 points in common. Parallel networks have the same voltage across them. A node is a point common to 2 or more networks of branches. Current entering the same node. Thank you very much. So we can forward our discussion on that. Then when we meet, we talk about